called Interstellar Travel, and it's somewhat ironic that we're all trapped at home at the moment, largely, and here we are talking about traveling across the cosmos to other stars and planets in our galaxy or beyond. But anyway, interstellar travel, will we ever be able to reach the stars? And the title screen here is from the movie Interstellar, with their rather interesting warp drive spacecraft that has gone out to visit the little planet there that's orbiting the giant black hole called Gargantua in their fictional tale. But bringing it back down to Earth, and credit to Brian Lister for a couple of these slides at the beginning here. This is one of his. If you were to travel at the speed of sound, 768 miles an hour in English money, 1,200 kilometers per hour in metric, then you would be the speed of one of these jet fighters here, which is just breaking the sound barrier and causing huge condensation in its shockwave. And that's a very high speed for ordinary earthly matters. So if you were doing that, how long do you think it would take to fly around the world once if you were traveling at the speed of sound? Well, the answer is just 33 hours. So just over 1 day to travel right around the Earth in a jet fighter. But of course, you wouldn't have enough fuel. You'd have to slow down and refuel several times in reality. But 33 hours take you around the Earth as long as you had the fuel for it. If you tried to fly right around the sun, and again, thanks to Brian for this slide, one lap around the outside of the sun, flying quite close to the surface, but just enough so you didn't get fried, would take you 147 days at the speed of sound. So it shows that the sun is really rather larger than the Earth. Suddenly these numbers are starting to get really quite big. And that's not the length of time to fly to the sun, that's flying around the sun. But what if we decided we were going to fly not to the sun, but all the way to the nearest star system? And that would be our nearest neighbour, the Alpha Centauri system. And it's a system of 3 stars. There's a very sun-like star, the yellow G-type star, the A member of the trio. The slightly fainter B member is an orange dwarf star, so a little bit smaller, about 70% the mass of our sun, and a little bit cooler. And then they are orbited much further away from their centre of gravity, but nearer to us, by a little red dwarf star, Proxima Centauri, so named because it is in fact the nearest star to the sun. And the distance from the sun to Proxima is 4.2 light years. Then we've suddenly changed units now to talking about the distance that light can travel in a year. So what is that? Well, a light year you can work out based on the speed of light. You're traveling 300,000 kilometers every second for a whole year. So if you multiply out how many seconds there are in a year, you get 365.25 times 24 times 60 times 60, which is 31,557,400 seconds. And if you multiply that by 300,000 kilometers, then a light year in round numbers works out at 9.3 with a whole bunch of zeros on the end of it, which I'm going to approximate as 10 trillion kilometers. That is a very large number indeed. And so the question is, for our jet fighter, if it magically were able to fly out of the Earth's atmosphere and continue on at the same speed and fly towards the nearest star, and let's also magically have it set off around about the time that Stonehenge was built in the Neolithic period, how far do you think it would have progressed from the Sun to Alpha Centauri in the intervening 8,600 years? Well, it won't really have got very far at all, because for 8,600 years at the speed of sound, I've done the maths for you, it works out at 1/100th of a light year. And so it's less than 1 part in 400 of the distance, despite traveling for 8,600 years at that speed. So you would just need to be traveling for a completely unfeasible length of time to manage to get there in a jet fighter. So we need to go rather faster than the speed of sound. Of course, we don't use jet fighters to go to space for the obvious reasons that they need to breathe air to burn with their fuel. What we use is chemical rockets, which take both the fuel and the oxidizer with them, and therefore don't depend on sourcing anything from the environment. And current rocket technology has a rough maximum speed that it could get to of about 100,000 miles per hour. So that's about 100 times faster than the aforementioned jet fighter in very round numbers. But I'm sure you could work out that it's still going to take thousands of years to travel to the nearest star on the basis of only going 1,000 times faster than an F-16. So here's a little schematic of a chemical rocket and the way it works. It carries its fuel and its oxidizer in the two coloured tanks, pumps them into the combustion chamber, ignites them, and they superheat and come rushing out of the exhaust at very high speed. And you can work out what the thrust of a rocket is going to be, and it depends purely on the velocity of the exhaust gas and the mass of the mass flow rate of the rocket and the pressure in the nozzle. There's a formula for it there. And you can work out an amount of thrust that a given rocket can give for a given design carrying a certain amount of fuel and so on. And it's measured in this unit called the specific impulse. And a rocket can give you about 500 in the specific impulse units. Okay, and we'll compare that with some other designs as we go forward. But we have got a few rocket powered probes that have left Earth and are heading out of the solar system. We have Voyager 1 and Voyager 2 that you'll all have heard of, and also Pioneer 10 and Pioneer 11 from a slightly earlier generation of spacecraft. They're all heading in different directions out of the solar system, out of the reach of the effect of the solar wind from the sun, which is really the edge point of the control zone that the sun has influence over. And where that solar wind runs out of puff is called the termination shock, where it is colliding with the interstellar medium, the thin gas between the stars, and it runs out of momentum and finally comes to a halt. And of those, they're all into that termination boundary shock region. And in fact, both the Voyagers have now overtaken the Pioneers because they're traveling at a higher speed and are the farthest out, and have officially left the solar system. So Voyager 1 was launched in '77 and is now 150 astronomical units from the sun. Neptune is 30, so that's 5 times further away than Neptune now. And it crossed the termination shock in 2004, so it's well outside the solar system now. And the termination shock turned out to be at about 100 astronomical units. And it's traveling away from us 3.6 astronomical units every year. That's 61,000 kilometers every hour. It'll carry on going and it'll reach the Oort cloud, that realm of the distant comets where things like Comet Neowise may have come from. And it's going to take about 300 more years to get to the Oort cloud. And Voyager 2 is not far behind. It was also launched in '77, and it's now 123 astronomical units away and moving slightly slower at 55,000 kilometers per hour. We know where the Pioneers are, but we're no longer in contact with them. We lost contact with them with their radios some time ago now, whereas we're still in touch with the Voyagers. And we should also mention the other deep space craft that we've got, New Horizons, which flew past Pluto and then flew past 2014 MU69, or Arrokoth as they've now named it, the little asteroid, the snowman shaped one. And that is traveling and going to leave the solar system as well. And it's doing 47,000 kilometers per hour now, so it's slower than both the Voyagers, but it's still on a similar sort of exiting the solar system trajectory. So those are some of the fastest moving objects that we've ever created, traveling at those sorts of speeds in the region of 60,000 kph, 40,000 miles an hour. Still not as fast as the theoretical best we could get out of a rocket, which would be 100,000, but still nowhere near enough to really sensibly go anywhere other than the solar system. What we need is more power in the propellant stage to accelerate the thing to go faster. And obvious one way of doing that is to use a nuclear source. If we go to a nuclear reactor and we were to take some propellant in the form of hydrogen, as in this schematic, and heat it by letting it flow over the very hot bed of an ordinary nuclear reactor, it would cool the reaction of the reactor and stop it from melting, but heat the hydrogen, and the hydrogen would come out of the nozzle at the back, having picked up a terrific amount of energy. And we reckon that a design like this can give us double that specific impulse. It gets us up to a figure of 1,000, so twice as much as a normal chemical rocket could achieve. But it's still not really very much in terms of the sort of numbers we need are not double that of a chemical rocket. We really want 1,000 times more. So people have looked at a variety of other designs. There's an Israeli team that realized they could do a similar thing using a different nuclear fuel, using the artificial element americium. Sometimes that's used in smoke detectors in the home in microscopic amounts. You'd have to collect several tens of millions of smoke detectors to have enough to build a reactor. But it can result in quite an efficient design of a nuclear heat engine, giving very high exhaust velocity and therefore getting us up from 1,000 to 2,500 on the specific impulse with this type of nuclear engine. And so that's beginning to get there. But other types of design using nuclear that have been around since the 1960s, there was Project Orion. And the idea of Project Orion was to build a spacecraft with a big shield on a lot of shock absorbers underneath it, as shown in the picture, and explode nuclear bombs underneath the tail. You just keep dropping another nuclear bomb out and blowing it up underneath your shield plate, and the force of the explosion would propel you forwards. And they took this very seriously for a while. The idea was even that it could drop small nuclear bombs to take off and drop a series of them, detonating them in the atmosphere and get itself up to orbit that way, and then carry on doing the same thing in space. But fortunately, both of those activities were banned with international treaties. The Interplanetary Treaty ban on nuclear weapons in space and the atmospheric test ban both put paid to this rather crazy idea, because just the amount of radiation would never have been tolerated. They did try and do calculations to suggest that it really would only add a very small number of extra cancers across the whole world if you launched a spacecraft. But just, you know, by the time they were talking about this, people were very anti any form of nuclear power anyway, so it was never really going to get anywhere, certainly never get off the ground. But of course, in the same way that an atom bomb, it was superseded by the H-bomb using nuclear fusion as its power, these sorts of designs, if they could achieve a nuclear fusion powered engine that would take tanks of hydrogen or heavy hydrogen, deuterium, and fuse it by crushing it together somehow inside a reaction vessel, could produce even better thrust than anything based on nuclear fission, partly because the weight of the fuel is so much less for the amount of energy that you get. And there have been a number of designs for fusion powered machines. Project Daedalus, and this particular one, Project Daedalus Icarus, was a two-stage nuclear fusion powered rocket. So the giant spheres here are the fuel hot containers holding hydrogen, and the big reaction vessel and the bell on the rear there is obviously the exhaust. So they would react the pellets of hydrogen or a continuous stream of hydrogen together, confining it with a magnetic field and zapping it with intense laser beams to trigger the fusion off, and the energy would heat the exhaust gas to tremendous temperatures and come rushing out the back. And the idea with two stages is that you can discard part of the apparatus once the main fuel tanks are empty, and you don't have to drag the dead weight of all the extra fuel tanks along with you. Here's another picture of the same thing. So, as I said, you can see labeled right in the center there, the pellet injector. So they were going to store liquid hydrogen in the tanks and then compress it down into little pellets and inject them into the fusion chamber, which was then either going to use lasers or electron guns or magnetic fields, or possibly a combination of them, to try to compress the material enough to trigger fusion and ride along on a beam of nuclear fusion powered exhaust. And this was being studied very intensely right through into the 1970s, into the 80s even, looking at what the technology could achieve. And if you could build a spacecraft like this, then you could probably get to one of the nearby stars, Barnard's star, 6 light years away, in 50 years. And 50 years is probably not an unreasonable time frame for keeping in contact with a space mission. Wouldn't necessarily be one that you would want to be part of the crew of going out for that length of time, but for an unmanned mission it might be possible. Unfortunately, the design of this spacecraft is for really quite a big machine. Here it is compared to a Saturn V rocket. Now, you would never build it on the ground and then try and launch it. You'd build it in space. But you can see that this thing is 50,000 tons of material that you've got to get off the ground. And each Saturn V was capable of lifting about 1 ton. So you'd need a lot of rocket launches to take up the raw materials to build such an immense machine, even if you could make it work. But if you could make the system work and you could get the hydrogen fusion reactor, as in this schematic, to work, generating this fusion in the center and the exhaust out of the back, contained by the magnetic field of the enormous coils that you've got going around it in this cutaway diagram, then it has a specific impulse of 130,000. So you will remember that that was a figure of 500 for a chemical rocket. This is 130,000. And so with this, you could continue to power your spacecraft and reach maybe 10 or 12% the speed of light. Very, very fast indeed, and a very worthy result in terms of traveling to the nearby stars. That's the sort of speed you need to reach. Another idea for this was not to bother taking the fuel with you, but to capture it as you went along, a so-called Bussard Ramjet, named after the man who suggested it. What he had was a fusion-powered tail on this thing that was doing all of the things we've just talked about, of fusing hydrogen together, but instead of a fuel tank, he had a giant scoop on the front, possibly with enormous magnetic field scoops around it to capture hydrogen from the interstellar gas and funnel it in and then feed it through, do fusion to it and have it come out of the back. And that design, when we use that in air breathing environments in the atmosphere, is called a ramjet, where you don't have a fan pulling the air in at the front. You just use the speed of the moving craft to capture the air and ram it into the nozzle in the front. And so this is called a ramjet for space. It indicates that it is not a pure rocket design because it's reliant on its environment for some of its fuel, and hence ramjet is quite a good name for it. And when I first heard about this back in the 1970s, I was quite amazed by the idea, but never quite convinced of the feasibility of it, because it always seemed to me that the process of capturing the fuel at the front with a giant dish, even if that dish was a magnetic mesh or something, you would be constantly suffering a degree of drag as you swept through the thin gas and tried to sweep it up. You'd be capturing that gas and it would sap your momentum continuously. And I thought that might make the process relatively inefficient. And indeed, the ultimate sort of hydrodynamic simulations with supercomputers, when they finally came along, tended to suggest that this type of design really wouldn't work. The effort you'd expend in collecting the fuel would probably exceed the value of the fuel that you collected in terms of power generation. So if you were trying to sweep it up with a magnetic field, you'd have to use so much electricity to generate that magnetic field that it really wouldn't be efficient at all. So what can we do to make our spacecraft go even faster than a nuclear fusion powered rocket? Well, we could use an antimatter powered rocket. Antimatter is the opposite partner of ordinary matter, where we have antiprotons with negative charge in the nucleus and positrons, which are anti-electrons, carrying a positive charge going around the outside of them. And if you marry up two particles, one matter and one antimatter particle together, then they annihilate via E equals mc squared. All of the mass m is turned into a terrific amount of energy, E, c being the speed of light and c squared being a very, very large number. You get a lot of energy for not very much mass, which is just what you want for a fuel. In comparison to fusion, this process is nearly 100%, well, it is 100% conversion of the mass. You lose some of the potential because it comes out in the wrong directions in the form of neutrinos that you can't focus. So you can probably get about 40% efficiency out of this. You get about 40% of the energy, whereas nuclear fusion gives you about 1.4%, something like that, of the starting mass turned into energy. And so with an antimatter powered rocket engine, you wouldn't need very much fuel, and you could get to 30 to 40% the speed of light reasonably easily. The only problem is that we can make antimatter. We make it 1 or 2 atoms at a time, and that's really not very much, because in a sugar cube you've probably got 10 with 20 zeros after it of atoms, and if we're making them one at a time with a particle accelerator, it works out to be the most expensive material ever. If you thought gold was expensive, well, antimatter is around about $10 trillion per microgram to manufacture. So unless we could find a better way of manufacturing the stuff, nobody's ever really going to be burning it in a reactor anytime soon. But there are some projects, theoretical projects going on at the moment, Project ICAN and Project AIMSTAR, looking at using antimatter in limited quantities to trigger nuclear fusion in ordinary fusion fuel. So it's a kind of hybrid engine between a fusion and an antimatter engine, and that might reduce the cost a bit, but it's still going to be prohibitively expensive, I think. So if we can't do any better than that, and we can't use antimatter because it's too expensive, we need to think in different ways. And one of them has been tried. This is Project Icaros, spelt differently. And this is a solar sail spacecraft using the power of light from the sun reflecting off of a square solar sail. And the probe was launched in the direction of Venus and has used the solar sail to provide some additional oomph, some additional thrust. Not a very big solar sail, 200 square meters, and it created a tiny amount of extra force, 1.12 millinewtons of force. But because that's free and doesn't need any fuel on the spacecraft, it's managed to increase the speed of the spacecraft by 890 miles an hour for nothing during its time. So it's a technology demonstrator, really, of the idea that you could not use traditional fuel, but ride on a light beam. And certainly this would be one way of delivering space probes around the solar system, if you don't mind too much how long they take, if you just want to do it very, very economically on fuel. So another project that's on the go at the moment called Project Light Sail 2. There was a Light Sail 1, a technology demonstrator, but Light Sail 2 went up in 2019, carrying one of these little tiny CubeSat payloads, and went up, deployed its solar sail, and has been using the thrust of the solar radiation hitting the solar sail to carry itself into a higher orbit around the Earth. And they're doing experiments with it to work out how to control it. To start with, they had 1 or 2 tricky moments with it tumbling and becoming uncontrollable, but that's part of the reason that you do these sorts of things, to see if they can be made to work. And then here we have 3 people: Yuri Miller on the left, Stephen Hawking, obviously, and Freeman Dyson. And this was the announcement of the Breakthrough Initiative. It's funded by Yuri Miller. He's a Russian billionaire. He put $100 million of his own money on the table and then tried to find additional funding from other sources to go with it, to attempt to answer that big question: are we alone in the universe? And there are various ways of doing that. Some ground-based radio astronomy, SETI type radio dishes listening for the possibilities of signals from space, but they also were looking at funding what they called the Breakthrough Starshot, which was an attempt to send a probe or multiple probes to the nearest stars and to try and reach them within 20 years. Now, to do that, you need to travel at 20% the speed of light, 1/5 of the speed of light, 4 light years, 20 years roughly. You have to allow for acceleration, and of course you have to think about whether or not you want to slow down when you get there, or whether it's just going to whiz past. But the speed, as it says, works out to be 140 million miles an hour. And the idea is to have your solar sail or your light sail attached to the spacecraft and ride on a laser beam. So you'd launch it up into low Earth orbit, then unfurl the solar sail and zap it with a laser from the ground. And so it would fly away from Earth, riding on this laser beam, being propelled by it. The laser beam carries energy, and bouncing the laser beam off the sail, especially if you make the sail nice and shiny, that's the best way. You can make the photons bounce back and transfer momentum to the light sail, and you can get to fast enough to reach Proxima Centauri in 20 years. So the idea would be you would put your satellite together, and you would have an enormous array of lasers on the ground. You need a gigawatt power station to power the lasers, and the can focus it onto the spacecraft. But there are a number of issues with this. One is that the laser can't see the whole sky at once because the Earth turns. As amateur astronomers, you know that things rise and set, and so you would have to have several of these laser arrays scattered around the Earth. They would have to take over from each other as each one became in the right position to provide the thrust to the departing spacecraft. But it's a much better idea than trying to fly to the stars with a rocket, because it doesn't have to take the fuel with it. The rockets need to use 99.99% of the available fuel just to get out of the solar system, in terms of climbing out of the gravity well. And most of the fuel is actually concerned with launching most of the other parts of the fuel, and hardly any of it ends up in the actual payload. But here we could launch the satellites into low Earth orbit, and then the fuel supply stays on the ground. Now, there are some problems with that much laser energy going up through the atmosphere. And so some people have suggested, well, it might be better to put the lasers in space and build a giant laser cannon in space that wouldn't have to suffer the depredations of traveling through the thick part of the Earth's atmosphere and giving it some difficulties of aiming and dispersion and so on. But I'm not too sure that I really want to see somebody building a giant laser cannon in space just to transmit a space probe like this. It would be a very efficient way of doing it. But we've seen this sort of design before in Bond fiction. There's on the left, from Diamonds Are Forever, it's Stavro Blofeld's laser cannon zapping the Earth, pointing the thing downwards. And in the later movie GoldenEye, the same sort of idea. I think it opened up and fired an enormous laser cannon down at people that were deemed to be the enemy. So, well, at least if you build one on the ground, you can't then turn it into a weapon very easily. Likewise, you don't want to build it on the moon and have somebody take it over and fire it back at the Earth. You could put it on the far side of the moon, but if you put it on the far side of the moon, then for 14 days, you might find that it was pointing the wrong way, and you wouldn't be able to power your spacecraft, which would cut down the amount of thrust by a factor of 2. So there's quite a number of issues with this whole idea of building a giant laser cannon. But the spacecraft they want to send look like this. They're called the Breakthrough Star Chip. It's a tiny credit card sized printed circuit board with some chips on it and a little sensor there for picking up some lights from the laser beam to power it. And it would contain all of the necessary electronics, processor, memory and radios to allow it to communicate back to us. And it would have small lasers on it that would be able to also be used to do steering. So it actually has the ability to steer as well as guide itself and talk back to us using the antenna in the form of the solar sail. So all of this is possible, and we should be able to make these in large numbers cheaply enough to launch not just one but a whole swarm of them. And the reason that matters is because if you're traveling at 20% of the speed of light and you hit a particle of dust minding its own business in interstellar space, the energy of that collision is enough to destroy the spacecraft in many cases. And so we would harden them as much as possible against impacts, but reckon to lose quite a large number of them along the way. And so the idea would be to launch maybe 1,000 of them in a swarm and power them all off one laser on the ground and just hope that some of them make it through to the destination. And that would work because they're so small and cheap. You could launch 1,000 of them on a modest number of rockets in the same way that Elon Musk has been launching his Starlink satellites, about 60 or 100 at a time, on his Falcon X rockets into low Earth orbit recently. So that demonstrates that the first stage works, and the solar sail projects that are going around the solar system prove that the idea of riding a light beam works and that the physics and maths are correct. All we need is the giant laser, and then unfortunately the giant laser is the expensive part. And so here's a little diagram with a logarithmic scale on it, showing the distances going through the solar system from the sun outwards. Neptune there at 30 astronomical units, Saturn at 10. The Voyager spacecraft, well, they're at 123 and 150 now, just outside that boundary, the termination shock and the heliopause, the limits of the sun's magnetic field. And they're on their way towards the Oort cloud, which goes from 1,000 to 100,000 astronomical units. And then it's very neatly around about 1 million AU to get a very long way indeed out into space on this diagram. But that's not really very helpful in terms of planning where we might go, other than the nearest star, Alpha Centauri. So how far is it? Well, here's a little plan of the possible route maps that you might take with your solar sail or your laser sail spacecraft with the distances on. You can see it's 4.3 to go to Alpha Centauri. Barnard's star is next at 5.9 light years. And then there are a number of choices. We could go to Wolf 359, another red dwarf star at 7.6. We could go to Sirius at 8.7 light years. Leyland 21185 at 8.1. Epsilon Indi 11.2, and others out beyond that. So the question really is, what out of all of these are the prime targets that we might want to go to? And I've listed what I think the prime targets should be for such things on the next slide. So obviously we should go to Alpha Centauri. There are 3 stars there, and one of them, Proxima, is known to have an Earth-like planet. So we have to send a probe there. But it would also be very, very interesting to discover if either A or B had their own planets as well, and to target a mission to fly by all of the members of the Alpha Centauri system. The reason I mention that specifically is because sun-like stars like A, are obviously of interest because they're just like our own. But B is an orange K1 type dwarf star, and these can be very, very old and live a very long time with a sensible habitable zone. And if I was to place a bet, I would bet that the first place that we're likely to find alien life is on a planet round a K-type star, not a G-type star, because of their very much longer evolutionary opportunity that they have. I'm very much interested in planets around orange dwarf stars. I'm not so interested in red dwarfs because they tend to have a very narrow habitable zone. They're a bit feeble, and the habitable zone has to be quite close to them, and they tend to have a lot of X-ray emitting star flares, which mean that planets that are in the Goldilocks zone, not too near and not too far, but just right in terms of temperature, tend to get bathed in X-rays from these flare star behavior of red dwarfs. So I'm not so keen on the red dwarfs. I definitely think the K-type ones are the place to look. So if we look down the list, the next one is a red dwarf, Barnard star. Well, yeah, okay, we could go there. We haven't really got any idea whether it's got any Earth-like planets, but it does appear to have a couple of planets around it from various studies. So could be good. The next one on my list is Epsilon Eridani at 10.8 light years. That's another orange dwarf star, and again, we think it has a probable planet and possibly multiple planets and multiple asteroid belts. And so that's a very good candidate for having some sort of habitable or inhabited or life-bearing planets there because of the age of the system. It's older than the sun by several billions of years. Evolution will have had a lot more time to do its thing. Very interesting one. Likewise, we've got the next one that comes up, Tau Ceti at 11.8 light years. It's a G8 star similar to the Sun, shown to have 5 planets. Well, that's the most Sun-like star and star system with planets that we know of nearby, so we really ought to include that one. Wolf 1061, well, that's a red dwarf with a super Earth planet in the Goldilocks zone, so that's worth checking out. And then Gliese 581, 20.3 light years, very famous one. This one, it's a red dwarf again, but planets G and D of its multiple planet system are both in the star's habitable zone, and G looks a bit like a roughly Earth-sized planet. D looks a bit bigger, and possibly with a bigger magnetic field and a stronger atmosphere, might be able to protect itself against the ravages of the aforementioned X-ray flares from its red dwarf parent. So I think that's well worth investigating. Gliese 667 is another red dwarf with yet more planets around it. And then finally at the bottom of the list, Trappist 1, very famously discovered with 7 Earth-like planets, some of which may have liquid water through being in the habitable zone, but that's also a red dwarf. So you can see the red dwarfs are dominant here. The only ones that are not red dwarfs, that are orange or yellow stars, so K-type and G-type ones, are the 2 members of Alpha Centauri, Epsilon Eridani and Tau Ceti. So those are my 3 favourites if I had to pick any, but these should be the ones we would target. And the question really is, how far could we get? And if we had a breakthrough Starshot aimed at these, which ones would be achievable? Well, let's say that we don't quite get to 20% the speed of light that they hope for. Let's work on the basis of 16% the speed of light. and give ourselves a 30-year time limit. And it turns out that with such parameters, you have to go to Alpha Centauri because the rest are out of range. You can't quite get to Barnard's star if those are your parameters. So you either need to go faster, which I'm not sure is very feasible, or you have to have put up with a multi-generational project. And if we go to 60 years and 16% the speed of light, then we get a bit more choice. And we can include Barnard's star, UV Ceti, Wolf 359, or Sirius, or Leyland 21185 in our choices. So it gives us several more interesting red dwarfs that we could visit. We could go to Sirius. Sirius wasn't on my target list, despite being relatively nearby, because it's only 250 million years of age as a star system. And that is far too short a period of time, really, for evolution to have done anything on any companion planets. Plus, we don't know that it's got any companion planets at this point either, so it doesn't make my favourites list. Okay, let's go to 100 years, and now we're managing to span most of these, and we can get to Epsilon Eridani and Tau Ceti, my two favourite other candidates, as well as a few of these others. Epsilon Indies, another interesting one. And these are around about that sort of 11, 12 light year distance. That's the sort of distance that really gets us into having plenty of choice and some nice interesting ones to go to. So maybe we go pick them off in order and go Alpha Centauri, Barnard's star for the first couple, and then, well, we're going to have a 100-year mission to go anywhere else. And so if I take my prime target list and chop it down and colour it in, yep, those 30-year missions, it's only those two nearby systems that we can get to. With a 60 to 100-year mission, we can do my two favourites, Epsilon Eridani and Tau Ceti, and also Wolf 1061, just. But we need to have a 150-year mission to make it out to the Gliese family at 20 plus light years, and it's going to take 250 years to get to TRAPPIST-1. So I don't think that's terribly feasible. No one's going to choose that until we've explored all the others. So it really turns out that even with these tremendously fast spacecraft doing a good fraction of the speed of light, 16% of the speed of light is no mean speed, we're really limited to the amount of exploring that we're actually going to be able to do. Now there is another idea, which is to build space probes that replicate themselves. With some of what we've got with 3D printing and so on, it's becoming vaguely possible to build a machine that can make copies of itself. And if you did this, you could send a probe out to a system that would report on that system, but mine the local asteroid field for more material to make copies of itself and make enough fuel, and then dispatch slow moving but multiple copies of itself to other solar systems. And provided they manage to spread, shall I say, like a virus with an R greater than 1, so that you got more than one probe for every probe, then they would soon fill the whole galaxy with space probes, and it would probably take around about 1 million years before they had spread out and covered a goodly fraction of the galaxy. And this is an idea that John von Neumann came up with, called von Neumann self-replicating probes. Obviously, you wouldn't send crews with any of these types of systems. And it's interesting that if we've thought this idea up, then it's probably been thought of by alien civilizations. And if they were much older than us, they would only have to be a million years or two ahead of us in the technological progression, and the probability would be we would start to see their von Neumann probes arriving in our solar system about now, and we haven't, and so we're very puzzled by this. Really, if there are other civilizations out there that might have had a multi-million or even 100 million year head start on the technology race compared to where we are, then there really ought to be their von Neumann probes falling out of the sky by now. So we wonder why that hasn't happened. Is it because we are alone in the galaxy, or is it because we are the first or one of the very early technological civilizations, perhaps the only technological civilization in the whole galaxy? Well, that's all part of the Fermi paradox, where Enrico Fermi, famous nuclear physicist, once said, "Where is everybody?" really hinting as to why we haven't seen their von Neumann probes falling out of the sky. Perhaps we have, and we've just mistaken them for something else. Who knows? So yeah, the idea is they could spread everywhere in a million years or so. There's one thing that I missed out here, which is if you travel fast enough relative to the speed of light, then you're going to notice the effects that relativity has on the behavior of time and distance. And in particular, it appears that a fast-moving traveler sees distances get shorter and sees less time elapse in direct relation. And in fact, if you traveled at 100% of the speed of light, time would stop and distances would appear to shrink to nothing. And so in 0 seconds, you would cover the whole distance as perceived by you. And so an example would be that if we had an astronaut and we sent them off in a spacecraft that very rapidly accelerated up to 90% of the speed of light, cruised somewhere, and then slowed down and returned after maybe spending a decent time examining some distant star system, then perhaps it might be such that it traveled 9 light years. It would take, from the Earth's point of view, round about 10 years to get there, traveling at 90% of the speed of light, and about 10 years for it to get back. And so we would see the spacecraft return after 20 years. But the traveller on it would have only experienced 5 years of life during each of the direction. And so they'd have aged, if they spent a year examining the target, they'd only aged 2 lots of 5 plus 1 years, 11 years in total. So this is called the twin paradox. If you had 2 twins, you separated them, sent one off on this space mission and brought them back again, then they would have aged and they would find that their otherwise twin was now effectively 9 years older than them in biological age. And this really is true. And it means that actually for a crewed mission, provided you don't really want to come back and provided you can travel at a very high speed, then you could use relativity to make the journey more palatable to the occupants of your spacecraft. Of course, you left on Earth would still have to wait the full duration. So if we could make a spacecraft do 90% of the speed of light, we could explore perhaps in these 100-year long missions and not have the astronauts die of old age before they arrived. In fact, if you go at 95 or 99% the speed of light, then you can have it, arrange it so that the astronaut hardly ages at all, which is what you need. You do have all the problems of not crashing into anything, and I think that is probably fundamentally an unsolvable problem, crashing into a tiny grain of dust. with a relative impact velocity close to the speed of light would be like blowing yourself up with a hydrogen bomb. So it's just not something you could cope with. The other idea is to build a truly vast spaceship and put a whole colony on it, and then fly to the stars and not worry about how long it takes, because it's going to be your distant, many generations down the line descendants that are going to get there, and most of the people will live out their entire lives on the Starship as it travels from one system to another. And this has been popular with many science fiction writers, the idea of these generation starships. And I think they got into the subject of, really, would it work? Would it make any sense at all in terms of the people who stayed behind? Because the chances are that 100 generations down the road on these starships, the reason that you set off in the first place will have been lost in legend, and you could easily find that they don't bother communicating with the mother planet anymore, and they all just goes dark after a while, and you don't know what happens to them. And I think that could be quite a problem for distant space travelers of whatever form. More speculatively, if we can ever master the some of the wackier ideas of general relativity, we could build a wormhole and use it to shortcut the distance from one point to another in the cosmos, and fly through the wormhole and use it both as effectively a tunnel from one point to another that would avoid all of the tedious space in between, and get us around in no time at all. And such things are theoretically possible, provided you've got a bundle of negative energy. You need some negative energy, energy that is less energetic than absolutely nothing. And we don't know how to do that. We've never seen it. Not even antimatter has negative energy. It has positive mass and positive energy. So no weirdness ever observed in physics can give us a clue as to how you would go about building such a thing, but the physics says that it is possible. So there's quite a conundrum, really. But if you could build a wormhole, then you can build half a wormhole and surf along on it in the form of a warp drive. This is the physics of Star Trek and their warp drive, and it's real. It's a real product of general relativity, that you could bend the space in front of you one way, compressing it and expanding it behind you, and sit in a little bubble of flat space, apparently stationary, not moving, but shuffle the space from in front of you round to behind you, using what's called an Albuquerque warp drive. And again, you need a lump of this negative energy stuff that we just don't think is there's any real way to possess such. But if you could, then a warp drive is entirely possible. And then finally, you've probably heard in the press about NASA and the impossible microwave engine, this bell-shaped microwave resonant cavity, this tapered cone on one end. They set up microwave electromagnetic waves bouncing around inside this thing, and claim that it produces thrust without any exhaust. Now, that is against all the known laws of physics, in that it's a perpetual motion type machine. It's not expending any of its mass, and it's violating Newton's laws in the process. But various people have built these and claimed that they work, and that they get a non-zero amount of thrust out of it. On the other hand, other people say they've tested them and that it's all experimental error and nonsense. I think I'm with the latter. I don't think it's likely that they work at all, but unless we try these things, we never find out. And I think they were talking about building one of these and putting it up in space and seeing if it could drive itself along and make acceleration, because in the earthly environment it's too hard to measure the effects. And so doing the experiment in the vacuum of space where there's no resistance is probably the way to find out. And if you could do that, well, then you can do away with all that pesky fuel problem, and have a very, very powerful engine that can just accelerate you to any speed you like, really, up to the speed of light, of course. So we're still limited to those relatively nearby star systems. I think that's the fundamental takeaway from this talk, is that unless we can travel faster than light through warp drive, or wormholes, then we're stuck with our human lifespans constraining us to exploring the nearest star systems, or sending out these multi-generation space arcs to float the cosmos and just sort of travel until they find somewhere where they might decide they wanted to set up camp. On the other hand, they might decide they just can't be bothered and stay on the spacecraft. I just don't think that's necessarily going to work. Anyway, that's the end of the talk for today, and I hope you've enjoyed that sort of examination of the possibilities of interstellar space travel.